Hey everyone, this is Mr. here. In this video, we're going to be looking at molecular polarity. So what I have here is I've got some salad dressing. In salad dressing, the main ingredients are typically going to be oil and some kind of water or vinegar. And we all know that water, oil, does not mix. So what's going on here? What is the reason that these two compounds do not mix very well? Well, let's take a look at what happens behind the scenes in terms of electrons. This is where it begins. We look at the bonding. And we already know this, that we have bonding electrons that are being fought over in molecular compounds, in covalent bonds, by the different atoms that are sharing those electrons. So here we're going to have two hydrogens, here you're going to have a hydrogen and a chlorine, and what you do is you look up the electronegativity for these to determine them. So let's look at this. So we've got hydrogen, you go to the electronegativity table, it has a value of 2.2, 2.2, and then you look at the difference in electronegativity. It's like, wait a second, it's going to be 0. There's no difference. That means that the electrons are nice, evenly shared between these two atoms. When you look at hydrogen chloride, it's a different story, because you look at this, you're going to have a value of 2.2 over here, but the chlorine has a value of 3.2. So when you look at the difference in electronegativity, it's going to be 1.0. And remember, when we look at this, difference in electronegativity, 0 to 0.5 means you have a non-polar covalent bond. 0.5 to 1.7 generally means you've got a polar covalent bond. Anything beyond 1.7 electronegativity difference is going to be an ionic bond. So that just kind of shows you, again, a quick review. So here we've got a polar covalent bond. Well, what does that mean? Well, that means that the electrons, let me just move this out of the way, are going to be very unevenly distributed in the hydrogen chloride. So remember, the difference in electronegativity for hydrogen gas is going to be 0. So beautiful, even distribution of the electrons. So we say that this molecule is going to be non-polar. So it's a non-polar molecule. That means it doesn't have any charge dense. When you look at hydrogen chloride, though, remember the difference in electronegativity was 1. What that means is the greater electronegativity element, that's chlorine in this case, is going to become a little bit negative because it holds onto those electrons a little bit more, those bonding electrons. And then the other side is going to be partially positive. So the hydrogen is going to be partially positive. And when you look at the whole molecule, because of this uneven distribution of charge, this molecule actually has a charge. This end's going to be negative, or positive, sorry, and this end's going to be slightly negative. So this molecule, because of the uneven electron distribution, is going to be polar. It's a polar molecule. So it has charged ends associated with it. And that explains why molecules are going to be dissolving in each other. So let's look at these situations here. So basically what you have to look at to determine if a molecule is polar or nonpolar is you have to look at the type of bonding that's present and also its 3D shape. So let's look over here. So here I've got acetic acid. So this is my acetic acid over here. This is water, and you'll notice that both of these have charged ends. They're polar molecules. So I have a polar molecule over here and another polar molecule over here, and we know that water and vinegar will dissolve. So that means that these molecules have some kind of attraction between them, so they can dissolve in each other. Here I've got water, which is a polar molecule, but here I've got a lipid, and there's no charges on here. This is a molecule that's no charge dense, so it's called a non-polar molecule. And the two are not attracted to each other. There's no attraction between these molecules, and hence they don't like to dissolve in each other. So that means that when you've got acetic acid and water, they can dissolve in each other. We say that they're miscible. That's the fancy word for when liquids dissolve in each other. And here the oil is going to float on a layer above the water. We say that it is immiscible. And the reason is simply because we have a non-polar molecule, polar molecule here, and here both molecules are polar. Okay, so now let's look at some polar molecules. So in polar molecules, what that means is that the charges, the electrostatic charges, are unevenly distributed. They're uneven. Okay, so unevenly distributed. We saw that earlier in water. Let's put that in here. See, unevenly distributed due to polar covalent bonding. So that's going to be important over here. And this gives polar molecules distinct charged ends, which are called dipoles. So the ends are called dipoles. Think of the poles of the Earth. The same type of idea. So we already saw here that we have hydrogen and chlorine. So we had a value of 2.2 for the electronegativity. This was 3.2 for chlorine. And the difference in electronegativity was 1, which meant that we had a polar covalent bond here. So it's a polar covalent bond. Again, it's a bit of a review. It's okay. And what that means is that the end that's more electronegativity is going to become a little bit negative, and the other side is going to become a little bit positive. And this results in the electrons moving towards and spending more time with the negative side. And that means that the electrons are unevenly distributed. They're not evenly distributed here. So we have a charged molecule. This arrow here, we call it a bond vector. So the bond vector points towards the atom that is more electronegative, that holds onto those electrons a little bit more in the bonding pairs. All right, similar thing happens over here with our water molecule. Now, water molecule, when you look at the electronegativity of oxygen, you're going to have 3.4. This is 2.2 and 2.2 for the water. So when you look at the difference in electronegativity here, it's going to be 1.2. And as a result, what's going to happen is we're also going to have a polar covalent bond. Okay, bond over here. And that means that we're going to have some charged ends. So what happens here? We have to be careful here. The end where you have the oxygen is going to be more electronegativity, so it's going to have a negative charge over here, so slightly negative charge. And the hydrogen end over here is going to have a positive charge for each of these hydrogens. And when you look at the bond vector, where the electrons are attracted, they're going to be attracted both towards oxygen. So these are the bond vectors. So again, they're pointing towards the more electronegative substance. But how about this? How about the whole molecule? The whole molecule is also going to have a charge. So the molecule, if you look at it, is going to be negative at the top here and positive towards here. So what we do, we draw another line here, and this represents the overall charges for the whole molecule. This is called the molecular vector. Let me put this in here. Molecular vector, just like that. And it tells you that this end of the molecule is going to be negative, this end is going to be positive. Just like before. The only difference here, we've got two of these bond vectors. They're both going towards the oxygen. Here we've got nitrogen. Now nitrogen has this funny shape. Remember, the reason it has this shape is because it has a lone pair of electrons up here that push the bonding electrons down. So it has this trigonal shape, so trigonal pyramidal shape. And that's why the hydrogens are down here. So now when we look at the electronegativity, we look at the electronegativity of nitrogen, it's going to be 3.0. Each of these hydrogens is going to be 2.2. So here, the difference in electronegativity is going to be 0.8 over here. Okay, and this means that we're going to have a polar covalent bond, just like we did before. So polar covalent bonding. And what that means is that we're going to have charged ends over here. So the nitrogen is more electronegative, so this is going to be more negative. And each of these hydrogens is going to be a little bit positive. And as a result, we're going to have these vectors. I'm just use a different color here. These bond vectors for each of these bonds is going to be pulling towards the nitrogen. So that means that each of these hydrogens, the electrons are being pulled more towards the nitrogen over here in this side. And as a result, the whole molecule has a charge. So we look at the vectors. They're all pointing in one direction. And that means that this end of the molecule over here is going to be negative, and this end of the molecule is going to be positive. So again, this is called the molecular vector. And these individual ones here, over here, they're called the bond vectors. So you'll be able to see it over here. Use a different color. So bond vectors. So the bond vectors combine to give you this overall. It's almost like a tug of war. So if you think of a tug of war over here, let me just show you the nitrogen. Can you imagine 3 ropes? And each of these ropes is being pulled towards this person over here. What's going to happen is this person is going to end up with that particular object. Same thing is true here. Nitrogen is pulling on those electrons. So overall, the electrons are being pulled towards this end, away from that end. So just to kind of clarify that a little bit. All right, let's do some fill in the blanks over here. So an arrow called a vector. Remember, there's 2 vectors. There's one for the bond, one for the molecule. Shows the direction which electrons are being pulled or attracted. So always towards the more electronegative atom. Oh, that's a long word. There we go. More electronegative. Now, sometimes some molecules like water have multiple charged ends or dipoles. So multiple, more than one. You can see here it has the hydrogens, or even here the hydrogens down here in the ammonia. So the overall charge is determined by the net or overall vector pull. And this is going to give you the molecular vector, the one we drew in red earlier. All right. Okay, so the whole idea here is we have differences in the charges. So we say that these molecules all have asymmetrical charge. So let's write this at the top here. Asymmetrical electron distribution. So this means that the electrons are spending more time towards one end than another. So now let's look at the opposite of this. We're going to be looking at nonpolar molecules. So nonpolar molecules, what they're like is, obviously they don't have any overall charge. It could be 2 reasons. You could have nonpolar bonds. So nonpolar bonds, remember, have no charges associated with them. Or sometimes you might have polar covalent bonds. So polar covalent bonds. And what happens here is the vectors might cancel each other. The poles are in opposite directions. So it's almost like the tug of war, and there's no overall winner. So we'll take a look at that as well. So let's take a look at oxygen over here. So oxygen, we look at the electronegativity here. You're going to have 3.4 and 3.4. So the difference in electronegativity is 0. There's perfect shear here. There's no unevenness of the charge distribution. So we see this is a non-polar molecule. There's simply no charges in here. Now over here with the carbon, now and the hydrogen is methane, we look at the electronegativity. So carbon is going to be 2.6, and each of these hydrogens is going to be 2.2. We've got 4 of them. And what that means is the difference in electronegativity here is going to be 0.4. It's not enough to meet the threshold of a polar bond. So there's no charges here either. So we have another non-polar molecule because the bond is going to be non-polar. Now let's look at the last one here. So here we've got boron trifluoride. So let's look up boron. Boron has a electronegativity of 2.0. Fluorine is, oh, we know this one, 4.0. So the difference in electronegativity here is going to be 2.0. Now, according to our little guideline, this should be an ionic bond, but there are some exceptions to that rule. So when you have some substances like this one here, even though you're 2.0, you're still have a polar covalent bond, but it's an extremely polar covalent bond. Okay, so this is an extreme polar covalent bond. So it's an exception to the rule. So there are a few of these. We'll usually let you know what these are. So what that means is that the fluorine is going to be very negative. Okay, it's going to have a partial negative, and the inside here, the boron is going to be positive. And we're going to have these bond vectors. They look like this. They're all going outwards like this. But here's the thing. In this case, we've got all three of these, these forces here, the attractive forces on the electrons are exactly the same. And they're all being pulled away from the boron. So think about this. If you had a three-way tug of war, who would win? Nobody would. Because the vectors are all going outwards and they're all even, there's no overall charge. So this means there's no overall molecular vector. Therefore, no overall charge for the molecule. And it is nonpolar. So that's why this molecule is nonpolar. And that's what I said. Sometimes these vectors, these pulls, cancel out, and you end up with a nonpolar molecule. So in all of these cases, you don't have an overall charge with the molecule. There's no overall charge here. So that's what nonpolar molecules are. So there's an even electron distribution. No charge dense. So you might have a polar bond, like for example here, or sometimes a nonpolar bond, but there's no overall charge dense. So no charge dense. All right, so let's summarize everything here. So here's what we have. So if I've got a molecular compound, remember a molecular compound is going to be two nonmetals together, so two nonmetals. And you look at the type of bond. If you've got a non-polar covalent bond, what's going to happen is there are no charges. And because there are no charges, there's no vectors, and the molecule is not going to have any charges associated with it. So it's nonpolar. So no bond vectors. Because the bond doesn't have any charges. It kind of makes sense. Then you might have this. You might have the following. You might have a polar covalent bond. If you have a polar covalent bond, what's going to happen is two things. One of the things that could happen is the poles, the bond vectors, all cancel. And if the bond vectors all cancel, there's no overall charge. So here we're going to put down bond vectors cancel. So therefore, there's no molecular vector or net vector. And the charges are evenly distributed. And that's true for both of these. Okay, so both of these are exactly the same. So this would be if you've got vectors canceling, or bond vectors cancel. Okay, so bond vectors cancel, you're going to have this situation here. Write that down. Now, the other thing that could happen is you might have these. You might have polar covalent bonds, but the vectors, the bond vectors, do not cancel. Oh, sorry about that. So what's going to happen here? The bond vectors do not cancel. And we saw an example earlier too with the ammonia molecule. So here we go. Here are my bond vectors. Oh, they should be going the opposite way. They're going upwards. So the bond vectors are all going towards nitrogen. And as a result, you're going to have an overall molecular vector in this direction. So the molecule is going to be negative and positive at this end. So here, the bond vectors do not cancel. And as a result, there is a molecular vector and the charges are not even. They're more at one end than the other, or uneven. You have charged ends. So you have a negative end and a positive end. Okay? And that's a little summary for you folks there. So overall, again, what's happening? You can have nonpolar molecules, nonpolar bonds. You can have nonpolar molecules with polar bonds if the vectors cancel, the bond vectors cancel. Or you can have molecules with polar bonds where the vectors do not cancel and you end up with charges on each end. That's it. So next video, I'm looking at a few examples. Take care.